In this lecture, I want to expand on our examination of non-experimental approaches to gaining knowledge in science. We've already talked about how manipulative experiments are really the only way that we can truly identify cause and effect in science. And in some cases, we can even be misled in those situations. Other approaches to gaining knowledge that are non-experimental include correlation analysis, quasi-experiments, and mensurative experiments. There's a number of reasons why we may choose not to conduct true or manipulative experiments, even though they're the gold standard. One is moral issues. A good example is cigarette smoking. Nobody has conducted a manipulative experiment to demonstrate that smoking cigarettes actually causes cancer, but I don't think any of us would question that conclusion. In our field, there's also moral and ethical issues around lethal removal of animals for experiments, for instance, to look at how density might impact reproduction and reproductive output, for instance. There are also logistical issues, which are huge in natural resource experiments. One good example, obviously, would be global warming. There's only one planet, so we can't randomly assign CO2 concentrations to a number of planets to look at how that might influence warming of the atmosphere. In something a little closer to home, many of the ecological treatments that we would like to apply often require very large areas. So if you want to look at the effects of acid rain, for instance, that would require relatively large areas of treatment to look at the effects on watersheds and so on, or large-scale pesticide spray programs, for instance, could also require large treatment areas, which requires a lot of money, which then makes it difficult to get a lot of replicates of those kinds of experiments. And there's a practical reason that our budgets are often small, so going a less expensive route to address a particular hypothesis is often the way we have to go. So wildlife habitat studies, we often go out and simply measure where different fish and wildlife species occur, measure the characteristics of the vegetation or the other parts of the habitat to try to build wildlife habitat models. We could bring those animals into captivity, build areas of different habitats to try to address this more directly, perhaps using experimental studies, but again, that would be very difficult and very expensive. And there's a fourth consideration that isn't addressed as much, and that is that in some cases we may conclude that a test of effect in the field may have a better chance of telling us what the effect is on a wild population than doing a manipulative experiment in captivity. And an example of that is when we were looking at the effects of West Nile virus on Swainson's thrushes. There had been some laboratory studies of the effects of West Nile on Swainson's thrushes, and they had found no effect on survival rate. But of course, they're maintained in fairly constant temperatures. They're given food and water ad lib, and therefore they may be able to survive infection from West Nile because they have very favorable conditions. You put that same bird out in wild conditions and you might find a very different outcome. This has also been suggested for tests of the effects of brucellosis on bison, for instance. Again, captive studies tend to show relatively minor effects, whereas in the wild we know it does have negative effects on reproduction. We tend to focus on things like correlation analysis and quasi-experiments when talking about non-experimental studies, but there's actually a variety of different ways that you can address a hypothesis using a non-experimental approach. And if you can use a variety of different approaches, that often gives you much more confidence that the effect you're seeing is a cause-effect relationship. So let's go through some of the examples that Anderson provided in his 1990 paper, and I'm going to add one more. The first is strength of association, or effect size. So if we see a big effect of a pesticide or a toxin on the size of some fish or wildlife population, we're more inclined to think that that is a true cause-effect relationship than if it's a relatively minor effect. A good example of this would be the effect of DDT on fish-eating raptors. We saw a strong decline in those species everywhere where DDT was being applied. Second consideration would be consistency of association, and this basically requires looking across many different studies and looking to see if the effect that is observed is consistent among those studies. Again, DDT would be a good example of situation where pretty much everywhere people looked for it, they did find an effect. Specificity of association refers to showing that there's an effect on a particular group that is exposed to some causative factor, which is not found in other groups which are not exposed. Good example of this would be white nose syndrome and effects on bat populations. Again, we find those caves where white nose syndrome has invaded, that numbers of bats have declined dramatically in most cases. Caves where it has not arrived have not declined. Temporality of association is another important way of looking at cause-effect relationships. So you can look at what happened prior to exposure and after exposure, and then what's called response to cessation. So if the pollutant or toxin is removed from the environment, do you see a population recovering? A good example of this temporality of association is the barred owl-spotted owl interaction, where we've seen declines of spotted owl populations across the range whenever barred owls have arrived in that area. And we're starting to see now where there are experimental removals that when barred owls are removed, spotted owls do respond and their numbers come back. So that is very, very strong evidence that there's a cause-effect relationship. Dose-response relationship, more exposure, more effect. Again, this has been shown in many studies of toxins like heavy metals and pesticides, that the higher the exposure, the greater the decrease in the affected population. The sixth point here is what's known as coherence of association. And basically what we're talking about here is consistency with results of other studies. And Rosebaum referred to this as harmony with existing knowledge of how the treatment should behave if it has an effect. So you may expect the effect of some pesticide to have effects on insect populations and on insect-eating birds and maybe mammal populations in that area. And perhaps if the insects that are being affected are pollinators, that could affect seed set in the plants that they pollinate. So this is the thing that we're talking about, is that where you make predictions in different kinds of situations, you're finding effects that are all consistent with the prediction that this particular toxin, say, is affecting a group of insects. And a last one that I'll add that is not in Anderson's study is what I refer to as plausible causal explanation. So basically what we're saying here is that if you're seeing an effect of some pesticide affecting a vertebrate population. If you take that chemical and you apply it to cells, say in the laboratory, do you see physiological effects of that pesticide on metabolic pathways, say, in the cells, which could then explain how that's affecting the animal populations? So looking at sort of a reductionist approach and saying, okay, is there really evidence that this chemical is disrupting something in cellular metabolic pathways that could explain the bigger picture situation that we're observing? So one of the best ways to explain these different approaches is to just go through an example. So let's go through one that I think we all could agree that we feel like there's strong evidence for a cause-effect relationship between smoking and lung cancer. And this is a case where virtually all of these kinds of approaches have come together to give us confidence that this is a cause-effect relationship. So first of all, the strength of the relationship. We know that lung cancer is 9 to 10 times higher among smokers than non-smokers. Consistency. Virtually hundreds, if not thousands, of studies have been done looking at different areas, different populations, and so on, and all have found a very consistent effect. Specificity. The increased rates of lung cancer are limited to smokers, and even another form of specificity is you can look at rates of cancer among smokers of cigars and pipes, for instance, which are smoking nicotine or tobacco that contains this compound nicotine, but they tend not to inhale it into their lungs. And what we find is that rates of mouth and throat cancer are much higher among that group, whereas lung cancer is not as affected. So nice example of specificity in that case. Temporality. If you look at the big picture in terms of lung cancer rates among the population in the United States, for instance, you see that there's about a 20-year lag between the big increase in smoking post World War II, for instance, and rates of lung cancer. And then when the Surgeon General report came out in the early 60s, making the link between smoking and lung cancer, and there's a big campaign to educate people and get them to stop smoking. Again, you saw overall lung cancer rates decline after a 10 to 20 year lag. And you can also see this effect if you look at individuals that have smoked for a while and then stop smoking, that their chances of lung cancer decline among those who quit relative to those who don't. Dose response. Lung cancer rates are 20 to 30 times higher among heavy smokers than those that don't smoke as much. Coherence. Here, looking at other kinds of effects like secondhand smoke, different rates in men and women that have different rates of cigarette smoking and so on, all point to the same general conclusion that if you're in an environment that has smoke, even if it's secondhand smoke, that will increase your chances of getting lung cancer. And then finally, a causal explanation. Laboratory studies indicate an increase in cancer in cells exposed to smoke and nicotine, again, providing that reductionist evidence, again, and that can be done in a nice experimental kind of approach, but it bolsters the bigger scale non-experimental studies that have been done. And just one thing that's interesting relative to smoking and lung cancer, R.A. Fisher, whose paper we read earlier and who's considered sort of the father of modern statistics, actually came out and gave congressional testimony suggesting that there was not good evidence for a link between smoking and lung cancer because no manipulative experiment had ever been done. And he suggested that there could perhaps be, say, a genetic propensity for those individuals that tend to pick up cigarettes and start smoking to also have a gene that predisposes them to higher rates of lung cancer. And so he argued that you cannot falsify that hypothesis without doing manipulative experiments. And of course, he probably got well compensated for his efforts by the tobacco industry for this. And I think most people would consider that not very ethical, but in the strictest sense, he's correct. There have not been manipulative experiments, and therefore we can't deny that there could be another explanation for the association that we've seen. Another area where that affects us all, that we can't use experimental approaches, is in the whole question of global warming. And it's interesting that a lot of the tactics that were used by the tobacco industry to combat the relationship between lung cancer and smoking have also been adopted by the those in the fossil fuel industry that are trying to deny the connection between CO2 increases and global warming. And since this is such an important topic that affects all of us, I thought I'd just run through some of these same approaches and talk about how the evidence for global warming is very, very strong despite not being able to do experiments. First of all, strength of association. There's been about a 1 degree Celsius increase in temperature associated with about a 40% increase in CO2. And if any of you have looked at the relationships between CO2 increases and temperature increases, there's a very strong association between the two. Consistency. Temperature records around the globe have shown increases, and also temperatures of oceans and water bodies have increased over the same period. Specificity. The rate of increase is unprecedented over the last 10,000 years. And though there have been slight fluctuations over that period, we've seen nothing like the increase in CO2 that we've seen over the last 50, 70 years and the associated increase in temperature. Temporality. Increase in temperature, again, coincides with increase in CO2. Wouldn't it be nice if we could decrease CO2 levels and show a decline in temperatures, but we're not seeing any real political will to do that right now. Dose response. Temperatures are showing are increasing faster with increases in CO2 concentrations. Coherence. Many studies looking at loss of ice from glaciers, loss of sea ice, increase in sea levels, species shifting northward, all consistent with this overall theory that the planet is warming and having multiple effects. And finally, causal explanation. We've known for over 100 years now that CO2 is a greenhouse gas, meaning that it allows short wavelength radiation to penetrate into the Earth's atmosphere. Once those short wavelength light waves hit the Earth and warm things up, they reflect back as ultraviolet or as infrared waves, which are absorbed by CO2 and tend to keep that energy in the atmosphere rather than letting it dissipate into space. And so it is essentially like putting a layer of glass around the Earth, which allows penetration of light in, but reduces the rate of heat going out, thereby heating up the Earth. summarize though, it's always important to be skeptical whenever either conducting or reviewing non-experimental studies. First of all, there is a much greater potential for confounding effects. And Anderson et al. Provide an example in the reading, but especially in the kinds of studies we're involved with in environmental studies, oftentimes where situations where you might have a particular pesticide being used in higher levels, you may have lots of other chemicals that are being used in that same area, for instance. So making sure that you are seeing the effects just of the compound of interest as opposed to effects from other compounds is something certainly that needs to be considered. And one way to try to address some of the drawbacks of non-experimental studies is to do matching studies. In other words, to try to match your areas where some compound is being applied or a heavy metal is entering a river with other areas that are similar in other characteristics. And we'll talk about this some when we talk about impact studies. But again, that makes intuitive sense. And especially in human health studies, if you're looking at the effects of some toxin in the environment, and you're looking at an association between the levels of that toxin and some health effect, oftentimes you'll find that areas where one toxin is at high levels, there may be many other toxins that occur in that area at high levels. This often tends to be associated with poorer areas. Maybe there's landfills that are placed next to a poorer neighborhood, and there could be lots of different chemicals that are being dumped into the water or the air in that situation. So making sure that the effects that you're seeing aren't just due to other characteristics or factors that are associated with the particular factor that you're looking at. And finally, as we've talked about, it really comes down to a weight of evidence approach. I think we all agree that smoking increases the rate of lung cancer, even though there has never been a true experiment done. But the weight of the evidence from all different kinds of approaches have made it very clear that there's a strong cause-effect relationship in this case.